Assalamualaikum students. So this is the last topic for chapter 6, Carnot heat engine, refrigerator and heat pump. So first we look at Carnot heat engine. So Carnot heat engine is a heat engine that operates on reversible Carnot cycle. So it is the most efficient heat engines compared to others. So we see here, let's see that we use the same reservoir for 3 different type of heat engine. So first we have a reversible heat engine, and we have, let's say we have a irreversible heat engine and impossible heat engine. So let's look at this. So your reversible heat engine will be the most ideal ideal case. So the equation is like this. So N is efficiency equals to 1 minus TL over TH. Okay. So 1 over your TL is 300 over 1000 K. So the temperature must be in Kelvin. So you will get 70% for efficiency of Carnot heat engine. And for irreversible heat engine, you will always have less than your reversible heat engine. So it must be less than. And for impossible, as the name said, it's impossible. So you cannot have a number efficiency that is more than your reversible, because the reversible is already the best possible efficiency that you can get from a heat engine. So the last one, so is if you get more, then it is impossible. Okay, so let's try this example. A Carnot heat engine receives 500 kJ of heat per cycle from a high temperature source at 652 degrees Celsius. So your TH is 652 degrees Celsius, and reject heat to a lower temperature sink at 30 degrees Celsius. Your TL is 30 degrees Celsius. So every time you see this kind of question, make a habit to draw the schematic diagram, okay, so that you can see what information you are missing. So determine the thermal efficiency of this Carnot engine. And B, the amount of heat rejected to the sink per cycle. Okay, amount of heat rejected is QL. So we want to look the value of N and QL. So first, write down the equation as in the previous slide. Okay, where is my so part A, and reversible is equal to 1 minus T H over TL. So make sure the temperature is in Kelvin. So, oh sorry, this is the other way around. It should be TL over TH. Okay, let's check. Okay, TL over TH. So your TL is 30. Okay, 30 plus 273 over 652 plus 273. Okay, in Kelvin. So plug in this in calculator, and you will get an efficiency of 0.672. Okay, so for part A. And for part B, the question asks for QL, amount of heat rejected to the sink. This is your sink, so amount of heat rejected is QL. So you need to use the relationship, okay, this relationship, QH over QL, this ratio is equal to, okay, for reversible, okay, is equal to TH over TL. Okay. So rearrange this equation. So we want to solve for QL. So QL will equal to, so bring this side to the other side. So TL over TH multiplied by QH. Okay. So QH, we have the value of QH, we have TL and TH, and we can solve for QL. So make sure to always convert your temperature to Kelvin. QH is 500 kilojoule. So plug in this value and you will get QL reversible equal to 164 kilojoule. Okay. So that's the answer for part B. So now we have looked at just now Carnot heat engine. Now let's look at the quality of energy. So when we're talking about quality of heat energy, you need to see the comparison. Let's say if we keep the TL constant, okay, for this example, we keep TL constant at 303 Kelvin, and if you manipulate the TH by increasing it to higher temperature, you will see that you will get a better efficiency as the temperature go higher. So the higher the temperature of thermal energy, the higher its quality. Can we use degree Celsius unit for temperature here? The answer is no, okay? You just can try. If you don't convert it to Kelvin, you won't get the same answer. Okay? If let's say you just plug in maybe 10, your TL is 10 and TH is 20. So 1 minus 10 over 20, you get 0.5. And if you convert 10 and 20 degrees Celsius to Kelvin, you will get 283 over 293. And you cannot get efficiency of 0.5 if you do the conversion to Kelvin. So the answer for this is no, you cannot use degree Celsius for efficiency when you're dealing with Carnot calculation. Okay, so now we look at Carnot refrigerator and heat pump. So in Carnot heat engine, we use the word efficiency, but for Carnot refrigerator and heat pump, we'll use the COP, okay? COP reversible. So this is the formula, okay? And same thing. So reversible refrigerator COP is, for this case, this is the best possible COP you can get. So if for irreversible, your COPR will be less than your reversible value. And if it's impossible, it's more. So you cannot get a COPR more than your reversible refrigerator of the COP for your reversible refrigerator. The concept is the same like Carnot heat engine. Okay, now let's look at this example 6.7. A heat pump is used to heat a house during winter by maintaining the temperature at 21 degrees Celsius all the time. The house is estimated to be losing heat, okay, at the rate of 135,000 kilojoule per hour when the outside temperature, your TL, drops to -5 degrees Celsius. So determine the minimum power required to drive this heat pump. So you want to look for the value of W in. So first, So this heat loss, this is your QH. Okay, so QH value. So first thing is from the COP equation, okay, we want to get the COP value first. COPHP is equal to 1 minus 1 over TL over TH. So your plug in your TL as -5 plus 273 and your TH is 21 plus 273. So solve it in calculator, you will get 11.3. Your COP of heat pump, you get 11.3. Then we use this equation to calculate for work input requirement. Use the relationship between QH and COP. Okay, so now you already have your COP value, and from the question already give you the QH, so you can calculate for W in. So here, since this is in kilojoule per hour, so you need to convert it to kilowatt. Okay, so it's per hour. Okay, down 1 hour equal to 3600 second. Okay, so you divide 135,000 with 3,600 second, okay, to get kilojoule per second. You will get QH as 37.5 kilowatt. So divide by 11.3. So your work requirement is 3.32 kilowatt. So this is the answer for 6.7 example. So in 6.8 example, we want to get a kind of refrigerator operate in a room in which the temperature is 25 degrees Celsius. The refrigerator consumes 500 of power when operating and has a COP of 4.5. Determine rate of removal from the refrigerator. Okay, your QL, and temperature of the refrigerated space, TL. So first, okay, where is my, okay, but QL is equal to COP multiplied by W in. Okay, COP is 4.5 kilowatt. So if convert this to from watt to kilowatt, so your QL is 2.25 kilowatt. Then TL, we use this formula, 1 over TH over TL minus 1. So you have your COP, temperature, and then you can calculate for TH. Okay, TL, sorry. TH is 25 plus 273. So your rearrange this equation and solve for TL. So TL you will get 243.8 Kelvin. So this is the answer for part B. So I hope you are clear. Please try to redo the example on your own and see if you can get the same answer as mine. Okay, that's all. Thank you.